let's remember where we are, what we're trying to do, and why we're trying to do it. So ultimately, as a specific example for the purposes of motivation, well, suppose I have a material that is from which a structure is going to be made of. So I know something about the material behavior. In particular, let's say the maximum shear stress it can possibly sustain, and that material eventually is used to build a structure, and that structure is subjected to certain laws that I can, let's say, calculate with the knowledge of my ME 231 class. And I'm concentrating at a certain point in the structure, and I'm wondering, well, is the material going to fail there or not? I know its strength, and let's say failure is going to occur because the absolute maximum shear stress that I can find at that point is possibly going to exceed a certain critical value that's associated with the material behavior. I don't care how the stress is calculated. I don't care where it comes from. It could be associated with isotropic, anisotropic, elastic, inelastic material behavior. All I care about what the stress state is, because all I've done, remember, is based, or it's just based on a given stress formulation, given stress state, and we don't really need to know how it was calculated. Now, so I'd like to calculate the, say, absolute maximum shear stress so I can compare it against a critical value that's provided. So now let's first agree that if I know what the principal stresses are, it doesn't matter how I calculate them. If I know what they are, we can always go and always draw the Mohr circle in all cases. So the Mohr circles is something we can always draw. So we will have three principal stresses. Well, let's say sigma 1 is there, sigma 2 is there, and sigma 3 is there. So associated with those three values, there will be three more circles, which are essentially, this is the first one, this is the second one, and then there is a third Mohr circle as well. So this Mohr circle looks at rotations within the 1-2 plane. This one looks at rotations within the 2-3 plane, and this one looks at rotations within the 1-3 plane. And we see that if the material is going to display some critical value of the stress, shear stress, the value that I should be comparing against that material property to check possible failure is this value over here, because the principal shear stress associated with rotations in the 1-2 plane, that's tau 3, and principal shear stress associated with the 2-3 rotations, that's tau 1, and with the 1-3 plane, there is a shear stress tau 2 that is larger than all of them, so that is equal to the maximum shear stress that I encounter at that point in the structure. And we can also call it the absolute maximum, in the sense that it's the absolute max among all the max values that I observe on each circle. So we'll just go ahead and call, whenever we are able to calculate the absolute maximum shear stress, so I'm just going to refer to it as the maximum one, and we understand that that is the largest among all the principal shear stresses. Now, again, going back, if I want to compare this value against some critical value, and if I find, for instance, that this value is less than that value, again, as a means of motivation, this is not necessarily the criterion that I might be interested in, but if that is so, if I find that it's less than a critical value, am I safe? Well, first of all, I need to check whether it's safe to within a safety factor. But apart from that, the fact that I'm safe here doesn't mean that the structure will not break apart. I need to check all possible points in the structure, and I need to make sure that at any point in the structure, the absolute maximum shear stress is not exceeded. Okay? The absolute maximum shear stress does not exceed the critical value that is associated with the material behavior. Okay, so that is the idea. That's why we're trying to do it. If I can do this at one point comparing against a critical value, I can do it at all points, and this way I can make sure whether the structure is safe or not. Now, therefore, let us all agree that if I know the principal stresses, then I know the answer to this critical question associated with failure. Now, to find the principal stresses, eventually, is it sufficient? Well, not quite, because what I'm additionally interested in is what the failure planes look like. In other words, where are they located? What is their orientation? For instance, if I'm talking about the normal to the plane, what are the direction cosines associated with that plane? So, for instance, here I know that the absolute maximum shear stress has to do with the rotations in the 1-3 plane. And with respect to the one direction, if I rotate, so if we rotate starting from the one direction about the two direction by an angle of 45 degrees in the physical space, 90 degree in the Mohr circle, then I will reach a plane where this value is observed, okay? So I know it's 45 degrees, but I know it's with respect to the one direction and with a rotation about the two direction. So, well, for that picture to make sense, I need to know what the principal picture is, and that requires knowing not only the values of the principal stresses, but additionally I need to know essentially what the orientations of these directions are. Okay, so the principal picture consists of the principal normal stresses as well as the principal normal directions themselves. Okay, so the principal picture, as soon as I know it, I know both where failure occurs with respect to the principal direction, but I know what that principal direction is with respect to in my three-dimensional space, which is typically characterized with some direction x, y, z coordinate system, right? So I know that orientation with respect to that, and I know my failure direction orientation with respect to that. So I need to rotate about the two direction through an angle of 45. So one goes there, one direction goes to indicates a new normal to a new plane on which this value is observed. So I know exactly where failure is occurring and why it's occurring, or if it's occurring for that matter. Now, therefore, the question is, if I want to know this, I need to know that. And to know that, of course, I need to know the original stress state. And the original stress state is given by a picture where, in general, there will be normal stresses as well as, I'm just very quickly sketching this, some shear stresses. Okay, so that's the original picture. From that, I obtain the principal picture, and from that, I can eventually draw the Mohr circles and complete that analysis. Now, going from here to there is a critical step. That step can always be accomplished, remember, using the eigenvalue approach. That is always a valid approach. Now, on the other hand, if we have simpler states of stress, then we can directly go for the Mohr circle and deduce this picture along the way. So one such case is the generalized plane stress scenario. If we have generalized plane stress scenario, I know that one of these directions is already principal direction, so I can directly go for the Mohr circle. And yet a simpler case is the state of plane strain that essentially will allow us to do a similar thing. All right, so we obtain a state of stress and we calculate it from the loads, and then we go for some, let's say, failure analysis. That is an important motivation point. Now, remember, this is independent of the material behavior and where the stress comes from. But eventually, our motivation is going to be the following. I'm going to load the material, and I'm going to load it within the elastic zone. It may or may not be isotropic, by the way. It can be anisotropic, but I'm going to load it in the elastic zone. And eventually, I'm interested in how far I can load, how far I can increase these loads before some type of failure takes place. So in other words, the stress state is most likely associated with some possible elastic stress state if it's a good design. And I'm just wondering how far I can push the loads before this, let's say, maximum shear stress reaches a value that is associated, let's say, with some sort of yielding behavior, which indicates onset of plasticity. So the stress state most likely is going to come from some elasticity calculation. But again, independent of where that comes from, I might also be interested in the following question. And that following question is as follows. Now, here I have normal stresses, right? And I have a geometric depiction of the stress together with all the components, tau, x, y, y, z, etc. So now suppose I was interested in not stresses but deformations. Okay. Now stress itself, remember, it is a matrix. So it is sigma x, sigma y, sigma z. Those are the normal stresses, and then we have the shear stresses x, y, xc, and then it is symmetric. Let's just write symmetric there, and then this is yz. All right, so now similarly, first of all, this strain, just like stress, has 6 independent components, and therefore it is indeed quite tempting to go ahead and try to write the strain as a matrix. Now with the stress, we've done so, and then based on equilibrium, that was the guiding principle going from that picture to that picture. Based on equilibrium, I was able to calculate the equations that govern what happens or how this picture is calculated explicitly in terms of equations or otherwise through eigenvalue problem, etc. So I was able to work out many things. Now the strain is also a quantity that has 6 independent components. So it turns out that we can also write it as a matrix. Okay? So this is probably the only time that we are ever going to write the strain as a matrix. So since we indicated the stress as such, I'm going to indicate the strain similarly using just one epsilon. So that's the strain as a matrix. And it will have normal components, epsilon x, epsilon y, epsilon z, and then it will have shear components. Now, here is a piece of information that goes just one tiny step ahead of the content of this class. And if we admit that step, the truth of that step, the rest is going to sort of follow. And that step is the following. When you put the shear strains into the matrix of strain, you put not gamma xy directly, which is the engineering shear strain, but actually you put half of it. And there's a reason for that. Okay, so that reason we're not explicitly explaining in the context of this course, although it's not very hard. Okay, so you put tau for shears for stress, but half the gamma for shears for strain. So this is going to be gamma xz half, and this is going to be gamma yz half. And I know that gamma yz or zy doesn't really matter, and therefore this matrix is also symmetric. So this is a 3x3 symmetric matrix, 6 independent components, 3x3, 6 independent components. We've written this as a vector involving these components. We've written that as a vector involving components, but without that factor of 2 because the Voigt notation does not incorporate that factor of 2. But when we write it as a matrix, for good practice, we almost always prefer to do so. So now that's the structure of the strain. Now, a small differential element can, for geometric purposes, can again be employed to depict strain. Now, these indicate force per area on this differential element. If I were to depict strain accordingly in a similar fashion, it would look sort of strange. I'm going to do it anyway with some caveats, with some care, with some caution. Just for the purpose of building a similar picture. Remember, this is quite unconventional the way I am depicting all of this, and physically I could eventually here talk about equilibrium, in other words, stress times that area is a force in that direction, etc. Here, all of that wouldn't make sense because strain times area doesn't really mean anything. But we're going to go ahead and do that anyway. So the most important thing I've told you so far is this factor of 2. When you talk about shear strains, just incorporate a factor of 2. But after that, if I go ahead and put the strains, so now let me depict these independently. So I will have normal strains, an epsilon x, an epsilon y, and an epsilon z. This is just for geometric depiction purposes. So that's the mathematical matrix representation. This is the geometric depiction. And then we are going to also have the shear strains. So here, there, and like this, like that, and so on. Okay. And every time when I put a shear strain there, I'm not writing all of them. It's just going to be a value gamma. That's the shear strain. Gamma. Okay. Something like x, y, x, z, etc. But every time they are, remember, scaled by a factor of 2. That's the correct quantity to put on this geometric depiction. Whereas here, we just go ahead and put the value of the corresponding shear stress. There are 6 of them, eventually 3 independent. Okay, so here as well, just the factor of 2 is there. So now, once we do that, now, could I ask a similar question? In other words, for instance, I could again say, well, mathematically, these things look very similar. So in other words, could I ask the question, well, is there a choice of surfaces, let me say, or mathematically a choice of the coordinate system such that with respect to that system, the components of the strain look as if they only have normal strains, okay, and no shear strains. So in other words, a similar picture. Is it possible that we find a picture, and now I'm drawing that picture curiously similar to this one in terms of orientation? That is not a coincidence. I'm going to make a comment on that shortly. Epsilon 3, so these are like now principal stress and these are principal strains. And there corresponding to these are some principal directions, which I will just indicate as 1, 2, 3 without distinguishing the two sets from each other for stress and strain for a reason again. So the question is there such a interpretation? Indeed there is, because just like stress, strain is also a symmetric matrix. Provided you interpret the shear components correctly with a factor of 2, then it turns out you can first of all plot a similar geometric interpretation just for visual purposes, and certainly afterwards go for some principal picture just like we did for stresses. On the other hand, and this is important, on the other hand, the picture that we ultimately calculate here is not going to be induced by equilibrium, because stress times area is a force, and then how do we calculate that picture? One way or another, we have equilibrium playing a role. Here, there is no equilibrium picture. Strain times area doesn't really mean anything. But eventually, it turns out, if you do the math correctly, all the equations that end up for stress transformations, in other words, transforming from that picture to that picture, also hold exactly for this transformation. In particular, for instance, you can, once you obtain that picture, go ahead and draw a stress. Just like a Mohr circle for stress, you can draw a Mohr circle for strain. Now, on that Mohr circle, the horizontal axis is the normal value, the vertical axis is the shear value. Remember, the shear value is always scaled by a factor of 2. Do not forget the factor of 2. So that's the correct interpretation of shear strain in this context. So then, suppose I would like to determine the absolute maximum shear strain by analogy. Now, just by the same discussion, let's all agree that as soon as I know the values of the principal normal strains, for instance, let's say they are epsilon 1 and epsilon 2 and epsilon 3. Notice that I'm not ordering them in the same fashion. It's not necessarily the pictures are identical with respect to the circles. So that would be one circle, that would be another circle, and that would be yet another circle. So in this case, what we are observing is that the is that eventually, so we have strain transformation. So in other words, I'm looking for instance, with respect to rotations about the 3-axis or within the 1-2 plane, what the maximum largest shear strain I can observe is, and that is a value of gamma, let's call it 3. But the value I observe here, this distance is not gamma 3, it's half of it. This is gamma 3 over 2. This value within the 1-3 plane, or that would be gamma 2 divided by 2, and that value would be gamma within the 2-3 plane, gamma 1 over 2. Okay, so compare that picture against that picture. It's the same interpretation, and I may wish to eventually compare that value against some value that is needed in design. So this would be, for instance, in particular, the absolute maximum shear strain divided by 2. So the absolute maximum shear strain in this case, in other words, is gamma 2. Okay, so this analogy, the mathematical background of this analogy is also something that we are not deriving explicitly, but just based on the fact that it's a symmetric matrix with the correct interpretation of shear allows me to carry on through this argument completely all the way to the end. So as long as I have the normal strains, then I can write that picture. I can draw the Mohr circle and I can identify the absolute maximum shear strain with respect to what? With respect to an angle of rotation that is 90 degrees with respect to the one direction, okay? And a rotation about the two directions. So I rotate about 2 and the one goes to a new direction, defines a new plane. On that plane you observe that maximum shear strain. And so in order to find that orientation, of course, I need to know the orientation of these principal strain directions. And the way to obtain that picture could be based on 2 methods. One, the eigenvalue approach. It's exactly the same approach that we followed in the case of stresses, except that eventually when you write the eigenvalue problem, just go ahead and plug in, instead of the normal stresses, the values of the normal strains, but instead of shear stresses, just plug in the engineering shear strain divided by 2. And that applies to the constants in the characteristic equation from which the principal values come and everything else. Okay? But if there are alternative methods, if there are simpler scenarios, in other words, if the strain state is not a very general strain state, then we could possibly go ahead and if it's not arbitrary, go ahead and calculate that picture in a simpler fashion. And that would be the case in particular if, for instance, the shear strains associated with the z direction, for instance, and for that matter any one of these directions, those 2 shear strain components would have been 0, and that would identify a state of generalized plane strain. So 1, you could certainly have an eigenvalue problem formulation, but 2, you can also describe the transformation through a state of generalized plane, not stress in this case, but plane strain. Generalized plane strain, let me draw it according to one of the conventions. I could pick any axis to be the axis associated with that generalization, but I'm going to pick the z-axis, so I'm going to say that epsilon z is not equal to 0, but gamma zx, let's throw in a factor of 2 as well for consistency, is equal to 0, and gamma zy is also equal to 0. So the strain associated with the remaining, with that direction, with z direction, is both of them, they are equal to 0. So there is only one shear strain in this case. In other words, gamma xy over 2, if you like, that is non-zero. And there's epsilon x and epsilon y. Okay, so this is the state of generalized plane strain. Now, there is also a state of plane strain. And in a state of plane strain, we additionally have epsilon z equals 0 in addition to having gamma zx and gamma zy equals 0. Of course, again, remember the discussion. This direction could have been x, y, or z. In any case, we have at most one shear strain that is not equal to 0. Okay, so if these are what I have as simpler cases, okay, these two, then I can directly go for the Mohr circle, because it turns out that that direction is the principal strain and the z direction is the principal strain direction. Okay. In this case, that value is 0. In this case, it's whatever the value of epsilon z is. And I can calculate the remaining 2 directions based on the Mohr circle once again. One thing that we have to immediately keep in mind, and it's very important, is the following. If we have a state of generalized plane strain. Does that mean that we have a state of generalized plane stress? Or let me ask a simpler question actually. If we have a state of plane strain, do we have a state of plane stress? Now that is a question that we can quite easily answer in the reverse direction. Now, as an example, I'm just going to write, because that's what we have presently, as an example, we can calculate epsilon z equals, if the material behavior, remember, is isotropic, then it's 1 over E sigma z minus nu sigma x plus sigma y. So if we have a state of plane stress, this is equal to 0, but as long as I have sigma x and sigma y, then epsilon z will not equal to 0. So plane stress does not imply plane strain. There will be a certain value of the strain, and therefore that's something I have to keep in mind. Conversely, a state of plane strain will not imply a state of plane stress in general, which is also something that we can easily show. Okay, and those I invite you to do. In particular, I invite you to show that if you have a state of plane strain, then the corresponding, if we have a state of plane stress, then the corresponding state of strain is generalized with the value being equal to, if we have isotropy, just carry on through the equations and you can show that this is equal to minus nu over nu minus 1 minus nu, so minus nu divided by, so this is too tiny, I can see in the video myself, it's nu divided by 1 minus nu multiplying epsilon x plus epsilon y. Okay, so if you have a state of plane stress, then you will have ultimately normal strains, and those normal strains can help you calculate what the third strain is. It's not a state of plane strain, it's a state of generalized plane strain. And alternatively, if we have a state of plane stress, then you can easily show actually what the value of the stress, of the corresponding stress is going to be. If we have a state of plane strain, then epsilon z is going to be equal to 0, and the fact that it's equal to 0 will induce sigma z equals nu sigma x plus sigma y. Okay, so what we have here is a state of plane stress but a state of generalized plane strain. What we have here is a state of plane strain, but what we have is a generalized plane stress scenario. But notice that a plane stress or strain setting is a special case of a generalized setting with that third value being equal to 0. And therefore, it's always true that generalized plane stress implies generalized plane strain and vice versa, but plane stress doesn't imply plane strain and vice versa. Okay, just be careful. So the generalized setting is always perhaps better to keep in mind. Remember also with respect to the determination of the absolute maximum shear stress, because we know that this third value, even if it's equal to 0, can influence the absolute maximum value of the stress and, for that matter, of the strain. Okay, so now presently also please recognize that I'm saying a lot of things. Some of these we are going to show explicitly, but what we've described so far is that mathematically we have a picture at our hands that is ultimately exactly equivalent to the stress scenario, including the methods, the interpretations, the details, the calculations, and the special cases. And further, as a special case, remember that we first started with plane strain, and in that scenario, we were able to calculate the functions of, for instance, of sigma x prime as a function theta of rotation about the z-axis within the xy plane, and we were also able to show, for instance, tau xy prime as a function of theta, so this was a certain function, and we were also able to show that sigma y prime I theta is simply a function that can be obtained by taking the function of sigma x prime, and instead of theta plug in theta plus 90 degrees or pi over 2. That takes you to the y prime plane, and it's the same equation with some terms being negated. So that was the case for stresses. So therefore, what we will be able to do now again is, that's the idea, everything applies. So just instead of this normal stress, we will write normal strain. And instead of that as well, we will write normal strain. But in these expressions, and explicitly over here, whenever we see a tau, we will instead plug in gamma half. And everything, again, remains the same. That half factor applies in the matrix representation, geometric, eventually Mohr circle, as well as in the equations themselves. So having said so much, I think we're at a good point where we can go ahead and actually directly demonstrate these ideas on a example, which is also of a lot of practical interest.